Hello.
Yes, sir. Good evening, sir.
Yeah. Evening. Okay. So today we'll start with the adjoint and inverse and
Yeah,
properties. So adjoint of a matrix, basically you know that it is the transpose of the cofactor matrix.
yeah,
So you find the cofactors and take the transpose. That is your adjoint. So it is given by the symbol adjoint of A, and you need to know ways to calculate the adjoint of matrices quickly. So for a 2 cross 2 matrix, you know the trick, right?
yeah,
What is the adjoint of it?
yeah. So you just give the diagonal constant and you put the negative sign for the other two diagonal elements and interchange their position.
So what is the other matrix?
Yeah, so in this case, it is A minus C minus BD.
No, that is wrong.
Sorry, it's, yeah,
You have to interchange the principal diagonal.
sorry, yeah, um,
You have to not interchange the other one and keep minus b minus.
yeah, it's the principal.
Do you understand what is happening?
Yeah, I usually don't remember it, but yeah,
You have to remember it.
yeah,
You don't have time to do adjoint of a 2 cross 2 matrix all the time.
yeah. It doesn't take much time, but yeah, that's right.
Every little bit of advantage counts in the exam.
Yeah,
You need to be able to write adjoint A of a 2 cross 2 matrix directly.
okay.
How do you calculate for a 3 cross 3 matrix?
Yeah, so basically you hide the row and column of a specific element and calculate the det of the square matrix that you get, of the 2 cross 2 matrix that you get, and after that you multiply it accordingly by minus 1 to the power I plus j.
That is the regular method of finding all the cofactors. That will involve finding 9 cofactors and then taking transpose.
Yeah, that's how you find it.
There is a shortcut method, uh, which is something again that will save time. Write down what I'm saying. This is the
Yeah,
shortcut method. You will copy down the matrix. Step one is just copying it down like this and just repeat the first two rows.
okay. I just note it down. Yeah.
This is step one. Do you understand what is step one?
Yeah,
Step two is take this A, B, C, D, E, F, G, H, I, A, B, C, D, E, F. And the first two columns you will copy down here. So it will be A, D, G, A, D, and B, E, H, B, E.
hmm.
So you're adding the first two columns. This is
Yeah,
step two. In step three, you are going to remove the first, you are going to basically delete this first row and first column, and
okay,
you are left with E, F, D, E, H, I, G, H, B, C, A, B, and E, F, D, E. And now from this, you will calculate EI minus HF, FG minus DI, DH minus EG. That will be the first three elements of your adjoint.
okay.
Similarly, HC minus IB, IA minus GC, GB minus AH, and finally BF minus CE, CD minus AF, AE minus BD.
Oh, okay.
So that will give you the adjoint, and obviously this will be faster than finding 9 cofactors and taking transpose.
Hmm. Yeah,
Find out the adjoint of, for example,
we'll just.
let's take an example. Find the adjoint of A is equal to 123,050 and 243. Find it by the new method.
Okay. Yeah. So I had one doubt in the last step. I could not note it down entirely. The last step where we do AE, like do
What
we
is
just
the
add
doubt?
it? Like I have not noted down the last step. I was writing it.
You have numbers like this.
Yeah.
You're doing AF minus BE.
Don't we write in step two? We write it as A B C A B D E F D E, right? Like, and so then what do you?
Why are you not paying attention to what I'm saying?
I was just writing it down.
What do we do in step 2?
Like we take the original step one. What do you call matrix? Or you can call it matrix, and then we just add the second and first column to it, like A B D E G H A B D E again. Oh, and then you hide it. Yeah. Okay. Got it.
Do you know what has to be done in each step?
In step three, we what do you call it? We do EI plus no EIFH. Sorry, we subtract.
What are you doing in step 3?
Yeah, so we write the three elements in each row, like by doing EI minus HF. That's the first element of the matrix, and we do it like that. And we continue. Next one
What
will be
is the
HC
second
minus
row?
BI. HC minus BI. I'll just
Find the adjoint of
yeah, I'll do it.
123,050,243.
Okay. Yes, I got it. It's 15 0 minus 10, 6 minus 3 0, minus 15 0 5.
Second, 15, 0,
Yeah, minus 10.
10, 12 minus 3, 6, 3 minus 6, 4 minus 4, and 0 minus 15, right? 0 minus, no, 5 minus 0. Now find the adjoint by the normal method, cofactor and transpose.
Yeah, I'll do that. Yes, I got it.
Is it matching?
Yeah, it is.
Cofactor here is 15, here it is 0, here it is 0 minus 1, so minus 10.
Oh, wait.
But you have to transpose it, right?
Yeah, it's not matching. Sorry.
Maybe we have to transpose at the end here. So
Yeah, I think so.
just check all the cofactors.
Yes, so it's matching with the adjoint according to the formula you give.
You know,
You have to take transpose of it.
6 minus 12, my
Yeah, you get the same values.
cofactors are matching, right?
Yeah, the cofactors are.
4 minus 4, okay. The cofactors are matching, so that means we have to do transpose at the end
Yeah,
because it is the transpose of the cofactors. So this method gives us the cofactors quickly.
yeah,
The advantage is that obviously this will be faster.
yeah,
So you need to know how to calculate adjoints. Uh, this method is valid for 3 cross 3. The other method was there for 2 cross 2 anyway, you know. If it
yeah.
is bigger than 3 cross 3 matrix, there is no shortcut method. You have to do by the normal cofactor method.
Okay.
Some properties of adjoint. The first one is basically if A is a square matrix of order n, then square matrix of order n, then A into adjoint of A is equal to adjoint of A times A is equal to det of A times In, where In is unit matrix of order n. So basically this property says that the product of a matrix and its adjoint is commutative.
Yeah.
The order of the product doesn't matter. It's same A adjoint A, same as adjoint A times A, and both of them are equal to det of A times In.
Hmm. Yeah.
So now this property you can prove by actually checking and calculating some matrices and see whether it is matching or not.
Hmm.
You can
Yeah.
try it out. Now from this property, we can deduce certain things. So first of all, if if A is a singular matrix, we know that singular matrix means that det of A is 0.
Yeah.
So therefore, A times adjoint A is equal to adjoint
Zero.
A times A is equal to the 0 matrix.
Yeah.
So in that case, you are getting this result. And null matrix you are getting. And obviously, it also shows you that the product of two and non-null matrices can be equal to a null matrix. All that has to happen is det of A is 0. You can easily say that A times adjoint A is null matrix.
Yeah.
We have seen earlier also that product of non-zero matrices can give you null matrix.
Yeah, that's right.
The second property is if A is a square non-singular matrix of order n, A is square non-singular matrix of order n, then we can say that the det of adjoint of A is equal to det of A to the power n minus 1. 1 second, just hold on for me.
Yeah.
Okay, this property you know how it comes, right?
Yeah.
How does it come?
Yeah. So we know that A into adjoint of A is det A into identity. So um, we can take the det of A into adjoint of A. So that's basically taking det A into identity. So you can take det A outside. You will, yeah, so det of identity. So then you can divide it as det A into det of adjoint of A is equal to,
What is the value of this
sorry, you
part,
can't
right hand
see.
side?
Yeah, the value of this is det A to the power n.
Here you can write this as, since it is a product of two matrices, you can always write it as det A, det B.
Yeah,
So you can
that's,
write it as det A and det of adjoint of A.
yeah, you take it to the other side and then it's n minus 1.
So you are getting this result that if it A is a non-singular square matrix of order n, det of adjoint A is this much.
Yeah.
Then in general, suppose there were many times you had to do this det of adjoint of
Oh, yeah.
A, and this adjoint was repeated n times. And A was a square matrix, non-singular square matrix of order n.
Yeah.
Then what will be your value for this?
Um, this one. Getting this. Adjoint of adjoint.
So far, what we have seen is adjoint of A
Yeah,
is,
we know. So first we need to get the result for det of adjoint of A. And then we can do it m
we
times.
already know what det of adjoint of A is.
Like adjoint of A. That's basically the same method only. When we get, we know that the value of det of adjoint of A is det A to the power n minus 1 whole square. So, so you can take another matrix with B as adjoint of A n m times. Yeah, so you'll basically get det A to the power, wait, n minus.
If you can prove this, then you can see a pattern.
Yeah, there's a pattern that I can prove that the n minus 1 whole square thing.
If you can see a pattern, then you can make a claim according to the pattern. This should be det of A to the power n minus 1 to the power n.
Oh yeah. Oh
That is
yes, I
the
saw the yeah, the pattern is simple. So you just have to see how many times adjoint comes. Like in the first case of det of adjoint of A, it comes twice. So we take it as n minus 1 to the power 2, where n is 2. And in this case, you're saying that it's happening m times. So it has to be, yeah, to the power m.
you will make this claim and you can prove this claim by induction.
Yeah, you have to keep, yeah.
You know what induction is?
Like you prove for one and then say it's true for all. Like,
What are the steps involved in proof by induction?
you assume something and then prove it right or wrong, depending on the situation.
That's not at all close to what induction is. What do you mean assume something and then prove? That's the
Like,
step involved in all proofs.
in induction, what we get the proof for one a certain case, and then we tell that it's true for any general case as well. Like,
You have never seen this before.
I have,
Have you done this in NCRT?
no, not in NCRT.
Where have you seen?
Like, once you proved a question using induction, as well as our sir also used it. So I've heard that term earlier in 11th. So,
How do you prove that 1 square plus 2 square plus n square is equal to n into n plus 1 into 2n plus 1 by 6? Do you know the proof for this formula?
um, I don't.
Can you do it by induction?
I'll try.
Well, try is not a
Not.
whether you
I'm not sure how to do it using induction though. Like,
so you don't know induction, you have to admit it first. No,
yeah, I don't think I know. I thought I knew it, but
find out how to do this by induction. This is not the topic of this class, so we will not be spending time on induction. But you need to
okay,
know the basic method of mathematical induction. It's a standard proof method that you everyone needs to be aware of.
okay,
If you understand how to prove this by induction, then you can prove this also.
yeah,
Right now, it's just a pattern. It's not a proof.
okay. Mhm.
You understand what I'm saying?
Yeah, I got it. Um,
The next property is if A and B are square matrices of order n, then we can say that adjoint of AB is equal to adjoint of B times adjoint of A. So when you take the adjoint of the product, it is same as taking the reverse product of the adjoint of B and adjoint of A.
Yeah,
Again, this can be proved, but the best, easiest way to check it is to take two small 2 cross 2 matrices. The adjoints are easily calculatable.
yeah, that's also there.
For 2 cross 2 matrices, you can easily calculate the adjoint, calculate the product, which will also be a 2 cross 2 matrix, calculate adjoint of AB, and check whether the product of adjoint of B times adjoint of A is matching or not. If you take arbitrary numbers, it is highly unlikely they will match by fluke.
Yeah.
Take arbitrary numbers here, then it is unlikely that this thing will match automatically.
Okay.
So you can check whether the property is correct or not. Or you can actually take unknown
You can
entries
do it
in the
without it. Yeah.
take unknown entries in the A and B and check whether all the elements are coming or not.
Okay.
The third property is if A is a square matrix of order n, square matrix of order n, then adjoint of A transpose is equal to adjoint of A whole transpose. So notice that these two things are different things. One of them is adjoint of a transpose matrix. The other one is adjoint of A and whole transpose at the end.
Yeah.
But both the things are equal. This is very
Yeah.
useful in problems. You need to know these properties.
Okay.
Fourth one is if A is a square non-singular matrix of order n, is a square non-singular matrix of order n, then the property says that adjoint of A is equal to det of A power n minus 2 times A. Now this property you have to prove.
Yeah. It's,
If you see,
you
take
know
the
that.
whole det, you will easily see that it fits the formula that we are getting earlier.
Yeah, it does.
How does it fit the formula? Take the whole det.
Well,
According to the formula that we saw earlier, it should have been det of A n minus 1 square,
n minus
right?
1 square. Yeah.
If I take det of the right hand side, it's like this, right? This is
Yeah.
like a constant, right?
Yeah. It's n times. So, yeah. N square
So
minus 2n plus 1. Yeah. It comes.
should become n minus 2 power n and then det of A,
N
right?
minus 1 whole square. Yeah.
So finally it is becoming det of A n square minus 2n plus 1. So it fits the earlier property which was talking about the det of adjoint of A. But
Yeah.
right now we don't have to prove that. We have to not talk about det. We have to prove the whole thing.
Yeah. We can do that as well. Yeah. So we just multiply. We know that A into adjoint of A is det A into identities. And over here, we need to find adjoint of A. So we need to multiply A into sorry, I'm getting confused. Yeah, we need to multiply adjoint of A into adjoint of A. Um, so from this result, we get adjoint of A into adjoint of A is equal to det of adjoint of A identity. Like we get that.
I don't understand. What is the first step?
Yeah, so we can take another matrix B as adjoint of A, and we can write the same statement as B into adjoint of A is equal to det B into identity. And over here, B is adjoint of A. So using that, we get the result. We just substitute another matrix.
So substituting B is equal to adjoint of A.
Yeah, and B into adjoint of B is det B into identity.
Right now in this result, if I put B as adjoint of A, I'm getting A times B is equal to
No,
B
no,
times.
I'm doing it in a totally different matrix. So we have defined a matrix B which is equal to adjoint of A, and we are finding the value of B into adjoint of B. Yeah, B into adjoint of B. Yeah, that's equal to det B into identity. So from here we get adjoint of A into adjoint of A is det of adjoint of A into identity. And we know that det of adjoint of A is det A to the power n minus 1.
So
Yeah, so n minus 2 into 1 second. So n minus 2 into A. Yeah. And we also know that adjoint of A, that side doesn't work. Yes. 1 second, sir. I'm just getting it. Adjoint of A into identity.
pre-multiply both side with A.
Oh yeah, yeah.
If you pre-multiply with A, what will this become?
Det A into identity.
You have adjoint
Yeah,
of A.
I forgot. Yeah.
You are getting this,
So you
and
can cancel it.
this
N minus
becomes that A n minus 2. It's a constant. You have A I n.
identity gets cancelled. Yeah.
Finally, you are getting this proof now.
Yeah.
Okay, so that is also a super important property. We now know what is adjoint of A as a simple matrix, and also what is the det of that.
Yeah.
Det of that, det of adjoint of A is, according to the previous property, it is det of A n minus 1 square. And adjoint of A is basically, we have got just now, it is this,
Yeah.
right? Okay, fine. Then the next property is, if A is a square matrix, if A is a square matrix of order n, K is a scalar quantity, K is a scalar, then adjoint of K times A is going to be equal to K power n minus 1 into adjoint of A. Again, this property we can prove by the original property, which was A into adjoint of A was equal to det of A into In. And here we will replace Ka for A everywhere.
Yeah.
Both sides, instead of A, I'll put Ka now. So it will
Okay.
be Ka-In, right?
Yeah.
So that of Ka we know is K power N, that of In, right?
Yeah.
And here you have Ka times this. I need to find just this much. So I need to obviously pre-multiply with A inverse, right? Or no, pre-multiply with
No.
adjoint A.
Yeah.
If you pre-multiply with adjoint A, you get K adjoint A times A, and adjoint of Ka. You will get this side K power N, that of A, and adjoint of A.
Yeah.
And adjoint A times A becomes that of A In, right?
Yes. Yeah.
That of A gets cancelled, K gets cancelled, it becomes K power N minus 1 adjoint of A.
Yes. Yeah.
So we get the proof for this. It is coming from this property by replacing A with Ka and pre-multiplying with adjoint of A.
Yeah.
Again, this property is super important. Uh, then the next thing is, what is adjoint of, if you have A is a square matrix of order n and you have m is a natural number, adjoint of A power m is same as adjoint of A whole power n. This
Yeah.
is true for m belonging to natural number where A is a square matrix of order n.
Yeah.
So power rule is pretty simple. There is not too much complication there. The next one is this one. If A and B are two square matrices of order n, A and B are two square matrices of order n such that B is the adjoint of A, such that B is equal to adjoint of A and K is a scalar. K is a scalar. Then that of AB plus K times IN, that of AB plus K times IN is same as that of A plus K whole power n. We need to prove this. So let's prove this. B is adjoint of A. So AB is what? AB is A times adjoint of A,
Yeah.
which is that of A times IN, right?
Yeah.
You can see that this is becoming that of A plus K whole multiplied by IN and that of that.
Okay. Yeah.
Inside this bracket, this is what it becomes, right?
Yeah.
So this is clearly that of A plus K whole power n.
Whole parent. Yeah.
Okay, so this property is not something that you need to remember, but you can see that it is happening, right?
Yeah.
Then the next property is a special case of adjoint of a diagonal matrix, of a diagonal matrix. Diagonal matrix is a matrix whose entries are only on the diagonals.
Yeah.
This is my A. Then we can say that adjoint is also a diagonal matrix. Also a diagonal matrix.
Yeah.
So
That's right.
the adjoint of this matrix, if you calculate, you will end up getting another diagonal matrix. Find out the adjoint. What is it?
Yeah. I'll just note it down. Yes, sir, I got it.
What method are you doing?
For this one, I used the normal method because there were only zeros.
Why are you not saying the answer?
I got the same answer. I got BC, AC, AB in as the diagonal elements.
You have to be
Adjoint of
fast.
A.
You have to be fast,
Oh,
faster.
sir, I got it. I got it a while ago. I just didn't tell it.
But
Um, oh, I thought I saw you working it out, so I just left it like. Yeah, I did get it a while ago.
the next topic is inverse of a matrix is basically only possible for non-singular matrices whose det is not equal to 0. If you have
Yeah,
a matrix A and B is the inverse of A and both A and B are square matrices of order n, then we can say that AB is equal to BA is equal to IN. This is the fundamental definition of the inverse. B is a
yeah,
matrix of inverse of A, which means A times B is equal to B times A is equal to IN, right?
yeah,
So then we can write that A inverse is equal to B or B inverse is equal to A.
yeah,
Now, since we have the result A times adjoint of A is equal to det of A times IN, we can see that in this situation, if I multiply by inverse on both sides, A inverse A adjoint of A equal to A inverse det of A IN. A inverse A should become IN.
yeah,
Adjoint
right.
of A is equal to this and this product is A inverse times det A. So from
Yeah,
here we are getting A inverse is equal
exactly.
to 1 by det of A adjoint of A.
Yeah,
A inverse is coming out taking 1 by det of A times the adjoint of A. And that's why the condition is that det of A should not be 0 for inverse to exist.
yeah,
Because otherwise you will not be able to divide by a det of A.
correct. Yeah,
That is your basic meaning of inverse. Now, there are several properties for inverses that you need to know. Every non-singular square matrix A has a unique inverse. By unique inverse means there will be only one particular inverse, not multiple inverses,
yeah,
right?
yes,
Then we have AB whole inverse will be equal to B inverse times A inverse. As long as as long as B inverse, A inverse, and AB inverse are defined. They are defined if all three of these matrices AB, B, and A are non-singular, right?
yeah, yeah,
So the product of two matrices, if you take the inverses get reversed, right?
yeah,
This is also true for any n variables also. ABC inverse would have been C inverse, B inverse, A inverse, and so on.
yeah,
The third property is if A is an invertible matrix of order n, A is invertible of order n, then A transpose inverse is equal to A inverse
Inverse trans-
transpose.
Yeah.
This is very important again because this means that we can interchange our two transpose and inverse operations easily. There is no
Yeah.
issue in that. So how do we prove that? We
You can again take a matrix of 2 cross 2 and prove it.
can prove it normally also. A times A inverse is In, and
Yeah.
if I take the transpose,
Of identity will be the same.
I will take the transpose on both sides. So A inverse transpose should be equal to A inverse A transpose. So because in transpose we know that it gets reversed, so we can write it as A inverse transpose and A transpose is equal to A transpose and A inverse transpose,
Yeah.
right? Now we can write this as A inverse transpose times A transpose. Both are equal to In.
Hmm.
Both of
Yeah.
these things are equal to In.
Correct. Yeah.
So that tells us that this thing is the inverse of this, right?
Yeah.
A inverse transpose should be the inverse of this.
It is. Yeah.
Why is it? Because we are getting the product
Equal
of
to
these two is
identity.
equal to identity.
Yeah. So it has to be the inverse.
So that is the proof of the original statement. We start off from here, we have gotten here.
That's right. Yeah.
Then the same property can be generalized a little. We can say A power k inverse, not the same property, this is a similar property, is the same as A inverse power k. This time it is powers and rest and inverses, not transpose and inverse.
Okay. Yeah.
And this can also be written as this. I mean, it is this is a notation. The meaning is this.
Okay. Yeah.
So the point is that you can, if you want to find A square's inverse, you can do it by doing A inverse and square.
That's right. Yeah.
That is the advantage. Uh, then the next property is obviously A inverses inverse is equal to A.
A. Yeah.
That is a trivial property. Then we can also say that det of A inverse, det of A inverse is equal to
One by
det
det.
of
Yeah.
adjoint of A by det of A.
Hmm. Yeah.
So what will be equal to? This is like a constant, right? This thing.
Yeah. We know that adjoint of, yeah. So basically, it'll be 1 by adjoint of A to the power n into det of adjoint of A. So it'll be det A to the power n minus 1.
Det of adjoint of A we know is this
Yeah.
times that's it, right? Divided
Yeah.
by
It's
det
just
A power n. This becomes 1 by det of A.
or you can prove it by like taking det on both sides for A into A inverses identity.
Hmm. That is also easier to do, but this is also coming.
Yeah, it's the same. Yeah.
Then the next thing is a special case for a diagonal matrix. Inverse of a diagonal matrix is also a diagonal matrix.
Yeah.
Diagonal matrix. The reason we are taking special cases for diagonal matrices is because in many problems they'll give you a diagonal matrix, uh, like the identity matrix, something like that, but with other numbers, not one. So
Okay.
you need to be aware of what happens in cases of diagonal matrices. So if you realize the det of this matrix is simply ABC,
Yeah, that's right.
so we know that this inverse is 1 by ABC times adjoint of this, and adjoint of this had come out as BCCA
Yeah.
right?
Yes.
So the 1 by ABC of that is 1 by A 0 0 0 1 by B 0 0 0 1 by C. So this is my inverse of A. A was a diagonal matrix 3 cross 3 like this. Inverse of A is basically simply inverting the diagonal element. All the other elements are 0, it remains 0 like that.
Yeah, that's right.
That is the special case for diagonal matrices inverse. Then we'll do some practice problems. Then the next thing that we have to look at is elementary row operations and transformations. Have they taught that in Alam?
Yes, sir, we're done with the chapter.
Did they do any row operations and all?
Yeah, they did everything.
For matrices or for determinants?
For determinants. And for matrices, like just the basic addition and subtraction kinds.
Okay. The next topics are
Um,
matrix polynomials,
yeah, I was not too thorough with that, not too sure of that.
matrix polynomials, Cayley, Hamilton,
Yeah, the later part of the chapter wasn't taught too well. Like,
eigenvalues, and finally this will cover in one class. The next class after that would be the class for solution of equations using matrices.
okay. So
So
from today onwards, I'm like beginning PYQs for math because I'm done with the module.
that's fine. We need two classes to finish the theory. So
Okay.
this will be the next class. This will be the last class for the theory. Have you
Okay.
started doing HCV for prostatics?
Yes, sir.
Have you read the chapter fully?
Yeah, I have read it, but I'm not done with the entire exercise.
Start doing the exercises.
Yeah, yeah.
When is your test?
My test is on 30th April, the mains pattern one, and the SRG exam is on 5th May.
Yeah. Physics, they have finished optics or they are still doing?
Physics, they are just left with what do you call the prism dispersion and chromatic aberration. Like only that is left.
And we continue in the next class
Yeah.
with maths only.
Sir, can we have class tomorrow at 4?
Sure, that's fine.
Yeah.
Okay,
Tomorrow is a
that's all for
holiday.
now.
Yeah.
Hmm.
Thank you, sir. Bye.